Last part of the session on quantum many-body systems. The first talk is online by Phan Thanh Nam. And Nam, are you there?
Yeah, I'm here.
Oh, very good. Okay, so Nam will talk about the Bogoliubov theory for trapped Bose gases. No, sorry, I shouldn't look at the screen here. They show the wrong slides. Anyway, sorry, I can't read the title from here, but Nam will talk about Bose gases and three-body interactions. That's what I remember. So please, go ahead.
Yeah, thanks, Robert. So let me share the screen. Okay, so I hope that you can see the slides. So first I want to thank the organizer, so in particular Robert and Stefan, for inviting me to talk today. I will report a recent joint work with Julian Ricord and Arno Trias, both in Munich. So the motivation of our work comes from the Bose-Einstein condensations. So this is the well-known phenomenon when many bosons at a very low temperature can occupy one common quantum state. And this leads to many interesting thin line superfluidity or quantum hypotheses. So this already predicted a long time ago by Bose and Einstein, but just observed in the lab in 1995. And from the mathematical point of view, then it's well known that if we consider a system with two-body interactions, then the condensate can be effectively described by the Grabitarsky functional. So here we get a nonlinear functional where the phi-4 term here stand for the interactions, so the short-range interactions. Today I will tell you slightly different pictures when we consider the system with the three-body interactions, and we will prove that the condensate will be described by the following nonlinear functional, where we get the phi-6 nonlinearities would correspond for the energy critical nonlinear terms. So this interesting from both mathematical and physical point of views. Okay, so in some sense, then the three-body interaction can be thin up like some kind of the correction to the two-body interactions. But in today, for simplicity, I will just restrict myself to the three-body interaction only. Okay, so here my n-body Hamiltonians. I will consider a system of n bosons in 3 dimensions described by the following Hamiltonians. We get the external potential would assume to be non-negative, locally bounded, and convert to infinity. So for simplicity, you can thin up the S-square potential. And we have the interaction potentials that scale in the following ways. And the function V, this non-negative, compactly support this about this and certify the three-body symmetries like here. So basically, we want to assume that the interaction potential of three particles at three positions S, Y, and Z will depend only on the distances between S, Y, and Z. And here we choose a very specific scaling n to the 1/2 in such a way that the rescale potential will have the scattering energies proportional to n to the -2. So I will discuss this later. And this is the so-called Grabitarsky regimes with the three-body interaction potentials. In this case, then the Bose gas is very dilute, and we're interested in the ground state properties when the number of particle n convert to infinities. Okay, so let me tell you the definition of the scattering energies. Here we consider the simple picture of the three particles. So we have the kinetic operator of three coordinates S1, S2, and S3, and we get the interaction potential. So we observe that the potential only depends on the relative coordinates S1 minus S2 and S1 minus S3. So let us do the chain of variables. We introduce the new variable Y1, Y2, and Y3 like that. Then we can rewrite the operator here like the second line. And you see that the rest of the operator is independent of the variable Y1. So if we are interested on the low-lying spectrum of the operators, then we can just take the variable Y1 frozen Put differently, we can remove the center of mass and restrict ourselves to the two-body operator here. So this actually some modification of the Schrödinger operator in 6 dimensions, where we reply the normal Laplacians by a weighted version with the matrix M given explicitly here. And given this notation, now I can define the scattering energies of a function V in 6 dimensions by the infimum of the following quantities. So we consider the kinetic energies with the modified version given by the matrix M, with the interaction energy by the V, and we require that the function F convert to 1 and S convert to infinity. So this is the definitions, and this is not difficult to prove that with our assumption on the potential V. Then the infimum problems defining the scattering energy has a unit minimizer, and this is given explicitly here. And this minimizer also satisfies the three-body symmetries, and this solves the so-called scattering solution, as I written here. Okay. So in particular, we can also prove that the function F between 0 and 1, and we can recover the scattering energy by taking integration of Vf. So from this formula, you see that you can just do the expansion, and you obtain the integration of V by the first bond series expansion, but there are also some correlation, some correction come later. So maybe just to compare with the two-body interaction case, I quickly remind you that if you have a function W from R3 to R, you can consider the two-body operators, Laplacian S1, Laplacian S2, and W S1 minus S2. Then, after removing the center of mass in the direction S1 plus S2, now you end up with a one-body operator here, 2 times minus Laplacian and V, and you can define the usual scattering energy in 3 dimensions by this formula. And we all know that this will be equal to the A pi A, where A the scattering length of the potential loop. So the definition that I gave you here for the potential in 6 dimensions is pretty similar, except that we get some weighted version of the gradient. So this comes from the removing the center of mass from the 9 dimension to 6 dimension. Okay. So now I'm ready to state the main results. So we can prove first that the ground state energy per particles, when n convert to infinity, will converge to the ground state energy of the Grabitarsky functional. Namely, we take the infimum of this nonlinear functional, where we get the phi to the shift coupled with the scattering energy of the potential, and we do the infimum with the mass constraint here. And secondly, we can prove the complete Bose-Einstein condensations, namely if the beside n is a ground state of the n-body Hamiltonian or some approximate ground state, namely the energy is equal to En plus some little of n, then the one-body density matrix converges to the rank 1 projections of the Grabitarsky minimizer. Okay. So actually we can prove that the Grabitarsky energy here has a unique minimizer, and this satisfies the following nonlinear equations. Right. So we also obtain some related results. So in particular, we might also consider the quantum dynamics and obtain a time-dependent result. So this already reported in the talk of Arnold on Wednesdays. We can also prove the ground state energy formula in the thermodynamic limits. In this case, then in the low density limits, we can obtain the leading order behavior. So this is similar to the 4 pi A rho in the Li Hong-Yong formula. And we might also consider shorter range, some sharper potential, namely we replace this potential by the potential of the form n to the 6 beta minus 2 Vn to the beta h with beta between 0 and 1/2, and we obtain a similar result, but we will not see the scattering energy of the potential V anymore. We just see the first bond approximation, namely the integration of V. So this case actually easier. Right, so let me make a quick comparison to the two-body interaction case. So this the case very familiar to most of you. So in this case, then we get the normal n-body Hamiltonian described by the pairing interaction potentials rescale in that way. And we know that the ground state energy will get the following expansion. So the leading order n is determined by the Grabitarsky theories. Okay, now the Grabitarsky functional come with the nonlinear term 5 to the 4, not 5 to the 6. And we also get the correction of order 1. So the leading order of the ground state energies was first proved by Lieb, Schrödinger, and Invasions in 2000. And a few years later, then Lieb and Schrödinger proved the complex BEC. In this case, then the next term of order 1 has been also recently understood by Bogoliubov, Brennecke, Sinet-Tiembo, and Slice for the system on the torus, and recently for the Trapped system in my work with Nachtergaele, and also by Brennecke, Slice, and Trapped. So I think the next talk of Brennecke will be related to that. I just want to mention that in the two-body interaction case, then the Bogoliubov approximation, namely the corrected reduction, predicted correctly the leading order. However, to understand the next order term here, and you need a qubit contributions. This change when you come to the pictures with the three-body interactions. So with the three-body interaction case, then the ground state energy will be like that. So the leading order n will be determined by the Grabitarsky theory with the 5-6 nonlinearities, like we proved. And we expect that the next order will be square root n and something order 1. And in this case, then Bogoliubov theories would fail for the leading order. So actually, to get the correct leading order, we need to see the qubit contributions, and the Bogoliubov approximation is more correspond to the next order corrections. So this somehow tells us that the three-body interaction case here is slightly more complicated than the normal two-body case. Okay, so in the last 10 minutes, then let me quickly tell you about some ideas of the proof. So first, for the upper bounds, then this is quite natural to think of some kind of the Jastrow Dyson drive state. Namely, we put n particles in the Grabitarsky minimizer, but we also add some correlations given by the scattering solution F. However, we are not able to compute or estimate the energy of this drive state. So in reality, then our proof is based on the following drive states. So we apply two unitary transformations to the vacuums. The first one, just a normal Y transformation, telling us that we basically put n particles in the Grabitarsky minimizer. And the second transformation here creates some correlations, which described by the qubit kernel S. So here S given by this expression, where again we see the Grabitarsky minimizer U0 and the scattering solution F. So this kind of state give us the correct leading order of the energies. And strictly speaking, then this is a grand canonical state, namely a state on Fock space. However, we can prove that the number of particles had a small variance, and using that, we can construct a drive state in the n-body space using techniques similar to what Jean-Philippe provided in his paper on the upper bound after one and two component charged Bose gases. Now for the lower bound, this is more interesting. Then we basically follow the overall ideas of Lieb, Schrödinger, and Invasion in the two-body interaction case. This contains up two steps. First, we use a Dyson lemma to replace the short-range potential by a longer-range one. So this is actually the main step where the three-body interactions case will be significantly more complicated. The second step, when we come to the long-range potential, we can apply some standard techniques of mean field approximation, for example, quantum definity theorems. And in the third step, we will actually prove a lower bound with some perturbation. Namely, we add to the kinetic energy by a range 1 projection of the Grabitarsky minimizer. And this allows us to obtain the complete BEC by a standard Hellman-Feynman argument. Okay, so let me now come to a little bit more detail with the first step, which is the most important step in the proof. Okay, so we have the following Dyson lemma. So this tells us that if you have a potential V non-negative, compactly supported, and the support contained in the small bonds operated are zero, then we can replace this by another potential U that's supported on some annulus operated R, which are much bigger than zero, where the integration of U is exactly the scattering energy of the potential V. And we had the following lower part. Right? So in the application, then the R0 much smaller than R1, R1 here should be R, and this factor should be very small. Then we replace the V by the U, and we sacrifice some part of the kinetic energies. So in the original lemma of Dyson's, then he played with the normal kinetic operator here, the absence, and he assumed that the potential V is radial. So in our proof, we had to extend the analysis to the non-radial functions. Moreover, we had to take care of the three-body symmetries, but this can be done by some nice relations between the relevant matrices of the symmetries here. On the technical side, we will only use the bars of the high momenta for the left operator here. But it's doable because if you restrict this operator to the low momentum bars, then this will be small by some kind of the uncertainty principle. Basically, when you localize both in S and in the B space, then the operator will be small. Okay. Now we apply the Dyson lemma to the many-body Hamiltonians. We have the following lower bounds. So this reads as follows. We had a parameter R much bigger than n to the minus 1/3 and much smaller than n to the minus 1/2. The claim is we can construct a function UR supported on the annulus operator R, satisfying the three-body symmetries, integration of U R equal to the scattering energy of V, and this satisfies the following lower bound. So the ground-state energy per particles of the n-body system can be controlled by the ground state energy per particles of an m-body system with an effective interaction given by the UR. Okay? So here the m is a parameter between n and 1 minus epsilon n. Well, for simplicity, you can think of m like n, but by a technical reason, we have to use this interval, and epsilon can be any fixed number between 0 and 1. And the kinetic operator S epsilon here, this is the one where we remove all of the high momentum contribution. So here we only get B square when B smaller than say epsilon minus 1. We also keep epsilon of the B square for the bubbles. Right. So the Dyson lemma here basically tells us that we can replace the potential V with the length scale n to the minus 1/2 by the potential U with the length scale R, which must better. So sorry, this inequality is wrong. Namely, R must bigger than n to the minus 1/2 and much smaller than n to the minus 1/3. Then on the technical side, when we apply the Dyson lemma, we would obtain a lower bound like that, but the potential UR will be coupled with a cutoff correspond to the situation when we want to ignore the contribution of the four body particles. Namely, we don't want to have four particles in the same radius of the side R. And to remove this cutoff, then we need to use a hit kernel estimate already done by Lind and Saringers. The estimate has the following form. So if we have any four body multiplication operator size, then the expectation can be controlled by the norm here. This will be small, and the exponential of the binding inequalities. So this is the difference of the inequality when we remove four particles. So if we can prove that this one here is small with m equal to n, then the picture will be much easier. However, we are not able to get an upper bound for the binding inequalities, and then we have to prove that for there exists some m in this interval such that the difference here is the one, and we can verify this lower bounds. So if we're in the two-body interaction case, then this basically close the pictures because the effective potential U here will be very nice. We can apply the mean field techniques to come to the Grabowski functional. However, for the three-body interaction case, then it's not quite because the potential here is still singular enough, and we have to do something else. So actually, we will try to replace the potential UR here by some longer range potentials, and that allow us to do the mean field approximation. Okay, so here again, I want to come to the constraint on R. First, we know that R must be bigger than n to the minus 1/2, such that the potential UR here is somehow longer range than the original potential V. But we also need that R must smaller than n to the minus 1/3 because the m-body system here is still dilute. And this is important to remove the four-body cutoff. Otherwise, then the lower bound here will be wrong. Then how can we replace further UR by another sub for potential? This is the content of the next slide. Then the conclusion here is we have the same lower bound, but now we don't put any constraint on the parameter R anymore. Or more precisely, now we allow the parameter R can be n to minus beta with any beta small as we want. Okay, and then this will be a very much mean field potential. Then we can just do the quantum definity theorem to get the conclusion. Right. So we prove this lemma by a bootstrap argument that works as follows. First, we use the bosonic symmetries to write the energy per particle of the m-body system like the energy per particle of an m1 particle system with m1 much smaller than m. Right, so m1 and m will satisfy some relation, but I will come to this later. Now look at this Hamiltonian. I will use the Dyson lemma to replace the potential UR0 by a potential UR1 with R1 much bigger than R0. So to do that, I need to use only epsilon bars of the kinetic energies. So this is very important because for the first step, we use already all of the high momentum bars, and now we cannot do this anymore. But in this step, we can use only epsilon bars of the kinetics. And this is doable because the potential UR0 divided for M1 square, this will be a very small potential. And in this case, then we can approximate the scattering length, we can approximate the scattering energies by the integration of the potential. And in this situation, we don't care about the constant we put in front of the kinetic operators. Okay, and this can be done if we require that the parameter R0 here, this must be bigger than M1 to the minus 1/2. And we need another condition that the M1 to the minus 1/3 must be bigger than R1. This condition just to make sure that after removing the UR0 by the UR1, then still we have a dilute system. And this is important to remove the four-body cutoff when we apply the Dyson lemma, like I explained before. Okay, and the series of the constraint here can be satisfied if we choose the R1 equal to R0 to the power 7/9. Okay, and at the beginning we can choose R0 anything between n to the minus 1/2 and n to the minus 1/3, and then we can just do the some bootstrap argument. Namely, in the second step, we choose the R2 equal to R1 to the 7/9, and so on. So in this way, we can mark the radius R as small as we want, as large as we want in these conditions. Okay, and when we have the operator UR, then this basically already in the mean field regimes, and we can do the mean field approximation like I talked to you before. Okay, so this is the end of the first step in the proof, but it's also the most important step. And I stop my talk here. Thank you for your attention.
Thank you, Nam, for this nice and also perfectly timed talk. We have a few minutes for questions or comments. Yes, please. Marcin.
Hi, Nam. I have a question. So if you go to the mean field limit, so beta smaller than 1/2, so can you capture the square root n correction? And how much simpler is the proof? I mean, can you get You don't have probably to iterate this argument.
Well, so to get to the square root n, either when beta is smaller than 1/2 or beta like 1/2 here, then we need to use the quadratic transformation like Bogoliubov. So we can do the further cubic transformation and then quadratic transformation to consistently renormalize it. But we still have to do on every step, like the input, and then we do the further step to get the refinement. Yeah, but honestly, then this is quite complicated, and we didn't have the full proof yet. So we just get the leading order fully at the moment.
Any further questions, Benjamin?
Can you show again the main result? I didn't.
Yeah.
Thanks.
Yeah, here.
Okay, so the condensation you don't have a rate for knowing how fast it condensates, or?
Yeah, we had some rate. So if we assume that the external potential like S to some power, then we get some small rate here, but not the optimal rate.
Okay, thank you.
Thanks.
Yeah, Andy.
Hi, Nam. I mean, my question is not so technical, but rather broad. So if you think about a system where you have molecule formation, so I mean, you have three-body interaction, you could assume that molecules are formed and you get another kind of particle afterwards. Is there any hope to do something in that direction? Does that sound reasonable to you?
Okay, so you mean the interaction potential is not quite non-negative, but some mixtures of the size.
Yeah, it's more like in the limit you have something short range, but you have maybe, I mean, you have three particles and two particles join and one particle goes out, and then, well, you have another sort of particle, a molecule with a doubled mass, and you describe it on two separate Fock spaces or so.
Yeah, so I think this could be doable. So namely, you get some mixture of the two bodies and three bodies. But the mixture is the interaction is on different length scales, right? So the two bodies to get the scattering length, you get the length scale 1/n, and three bodies you get the length scale 1/n to square root. Then I think we can apply the unitary transformation because the kernel this almost a commute. Then in this case we can just separate the contribution of the two. So I optimistic that can be done.
Thank you.
Any other questions or comments? Yeah, I see one over there. Yeah, go ahead.
So I have a question regarding the cubic the initial data. Oh, sorry, this is not time dynamics. So when you applied the cubic transform to the vacuum, then you applied the Weyl transform. So I want to know, if you look at that, how close does it compare to a coherent state if you take n to be very large?
Well, if you had a coherent state, then you just do the Weyl transformation, right?
Oh, no. I'm saying you have the cubic transform applied first to vacuum, then you apply the Weyl transform. So this part is not a quasi-free state in general. So, but I want to know how close is it to a coherent state?
Coherent state, you mean you
just the Weyl transform applied to the vacuum.
Yeah, but I think in norm then they are not close. So they had the same one body density matrix or close in this topology, but not close in norm and not close in terms of the energies. Right. So you just apply the Weyl transformation, then you get a wrong factor of the order n here. Right. So actually we also try the form like that, but with the cubic, with the quadratic transformation by Bogoliubov theories, but it's still not enough to get the correct leading order here. And all of those states, they are fair in norm.
Yeah, thanks, Nam. I think in the interest of time, we have to leave it at that. So I suggest we all thank Nam once more for this nice lecture.
Thank you.
And we continue more or less right away as soon as the setup got switched. Okay, very good. So our second speaker this afternoon is Christian Brennecke, and he will talk about Bogoliubov theory for trapped bosons in the Gross-Pedievsky regime.
All right. Hope you can hear me. So first of all, thanks to the organizers. In particular, thanks to Stefan and Robert who organized this nice thematic session. I'm very honored to be able to speak here. As Robert just said, I want to talk today about Bogoliubov theory for trapped bosons in the Gross-Pedievsky regime. And all the works I'm talking about is joint work with Benjamin Schlein and Severin Schraven, who's a graduate student or about to graduate at the University of Zurich. I tried to prepare a talk which is a bit more broad, so necessarily there will be some overlap with the nice lecture of Jan Philipp earlier today and also Nam's talk. So for the experts, already some apology for the overlap. I hope it's not too much repetition. Okay, so let me start with the setting and the questions we want to answer or we want to analyze. We consider n-trapped bosons in R3 with a Hamiltonian, as described here in this line, has a kinetic part, the sum of the kinetic energies. We trap the particles with an external potential, and we consider two-body interactions with a particular scaling, the GP scaling. And since we consider bosons, the two-space, that's the appropriate space is the symmetrized L2 of particles moving in R3 with n particles. Okay. Also, I try to keep the technicalities somehow to a minimal level. I mentioned here some important assumptions on the external potential and the interaction. We have a trapping potential, so we want this to be bounded from below, and certainly want to have it that it diverges when modulus of x tends to infinity. And we have also repulsive interactions, radial. For the rest of the talk, maybe it's also useful to just think about it like a smooth compressible function, something which is very simple and regular. Okay. Also on the external potential in the current paper, or at least one of them, we have some technical growth conditions, but I'm not really going to talk about this today. As I said, the scaling of the interaction, this factor n squared v scale n, corresponds to the GP regime, and it ensures that these two main contributions, the kinetic part in the energy and the interaction part, are of the same order in n. Okay, I'll talk more about this. Maybe you can already guess why this is the case from Jan Philipp's talk, but I'll explain this a bit in a couple of slides. What we can also keep in mind is that this interacting system is called ultra dilute. You can think about this in the setting with m particles in a region trapped of volume order 1. So the typical distance between two particles is of order n to the minus 1/3, but you see that the range of the interaction is only of order n to the minus 1, so much smaller. Okay, so on the one hand, we have very strong interactions due to this factor n squared, and at the same time, interactions are very, very rare. Okay. The questions we'd like to understand a little bit to a certain degree is, of course, what is the ground state energy? What's the bottom of the spectrum of this Hamiltonian in the thermodynamic limit? What can we say about the ground state vector? And what can we say about the excitation spectrum, the spectrum of the Hamiltonian above its ground state energy? Okay. So I want to start very slowly, and just to give some intuition on these questions, let me start with a trivial case where you don't have any interaction in the setting. Okay. In this case, everything is, of course, computable. We can reduce the many-body problem to a one-body problem. For instance, the ground state energy per particle is just the minimum of a one-body Schrödinger operator, just minus Laplace plus a V external, just because we can take product wave functions in this way reduce the many-body problem. We also have, of course, explicitly the ground state vector. You just take the ground state of the one-body operator, and you take the n-fold tensor product of it, because we have bosons. So what this means in particular, I'll give later a more precise definition also for the interacting case. But if we want to measure an observable, let's say A, which measures a property of, say, k particles, k fixed particles, then the expectation of this observable in the ground state vector is actually completely determined by the expectation of the observable B that we measure, and this is determined by the one-body state psi. Okay? So we have a large system, n is very large, but everything still is computable in terms of a one-body state. So what we call this is the phenomenon of Bose-Einstein condensation. Okay, just for the heuristic understanding of it. As I said, I'll give a more precise definition later, also for interacting systems. And of course, the higher eigenvalue is also clear. As I said, we have product wave functions as the eigenfunctions. So if you want to have higher eigenvalues, you just take products of one-body states of one-body eigenstates of the one-body operator, symmetrize them, and then you get the spectrum and also the eigenfunctions of the higher eigenfunctions for this many-body Hamiltonian. Okay. All right. Now let's turn to the interacting case. And the question is, of course, what happens when we turn on this weak interaction? And to start with, I mean, the simplest thing we could do, just to get a guess for the ground state energy or its leading order, is we could hope that since we have a weakly interacting system, the interaction is kind of a perturbation of this free part. Okay, so we could still hope if we plug in product wave functions into this Hamiltonian, evaluate the energy, that this will still yield the leading order contribution to the ground state energy. Okay, so this is what I do here in these first couple of lines. I take a product wave function, symmetrized, plug it in, and evaluate Hn, and then you get a nonlinear functional. You see you have here this delta-like function, n to the 3v scale n. I mean, this tends to a delta distribution of mass, the integral over v. And our prediction would be that the ground state energy per particle is approximately equal to the minimum of this nonlinear functional here. Okay. One important feature which makes this GP regime very interesting, or why we find this interesting, is that this prediction, the simple prediction, is of course very wrong. Okay, so we also have to take into account particle correlations which have the effect to lower the energy to leading order n even. Okay, so this prediction is wrong, and instead of considering product wave function, it's rather appropriate to think of the ground state wave function to have like a part which describes the condensate, which is still a factorized state, but then you also have these correlation factors here. Okay, we heard a bit about this earlier this morning on Philip's lecture, also in Nam's presentation. So let me still recall how we model the correlations. This is related to the two-body problem, essentially. We want to model the correlations by the solution of the zero-energy scattering equation. Let's also introduce the scattering length. So what we try to find here is you take the potential, which is unscaled in this case. You solve the zero-energy scattering equation minus Laplace plus a half v times f is 0 with a boundary condition at infinity. Then one observation under the assumption that we have a complex supported potential is that the solution looks for large enough x, like 1 minus a constant over modulus of x. This constant A0 is determined by the potential, and it's called the scattering length. Okay? What we also heard already in Jan Philip's talk is that when you take the integral of the interaction against this scattering solution, you get back the scattering length, and this 8 pi A0 is also strictly smaller than the integral over v, which would be just the leading order of the Born approximation of the scattering length. Okay. Right, and I also should mention, when we consider the scaled case, like in our Hamiltonian, many-body Hamiltonian, the corresponding scattering solution is just you take the solution of the unscaled problem and you also scale it with n. Okay, just by, scaling can compute it. Okay, so taking into account these correlations, when you think of the ground state like consisting of pairs of correlated particles instead of like pure product pairs, suggests the heuristic that the ground state energy per particle is given by a different functional compared to the one I stated earlier, namely the Gross-Piotrowski functional. Okay? Instead of having this constant 1/2 v hat of 0, we plug in here 1/2 the integral of v tested against f, which leads to this factor 4 pi a naught. And the idea is then through the correlations that this interaction is modified, the delta-like potential n to the 3 v scale n is replaced due to the correlations by n to the 3 v times f scale to the n. So this is a new delta-like potential, and it has the right mass. Okay. This heuristic prediction is actually correct. Nam stated this also in his talk. It has been proved in an important work by Lieb-Saringer and Ingwersen in 2000. It's a while ago, where they proved this statement that ground state energy per particle is converging in the limit n to infinity to the minimum of the Gross-Piotrowski functional. I also wanted to mention related works in a different setting, and Philip also mentioned them this morning. Works by Dyson about the leading order ground state energy, and Lieb and Ingwersen from '98, which are in the thermodynamic setting. So you have particles in a box, and you compute the ground state energy leading order in that setting. Okay. The next question I was asking was, what about the ground state? More precisely, what about condensation? This was also proved. Let me recall what condensation means. If we have a many-body state psi n, then we define its one particle's density matrix in the usual way. You take, you trace out the last n-1 particles from the projection onto this n-body state. Then you get a non-negative trace class operator of trace 1 with an explicit kernel. And the important point to see is that if you measure a one-body observable, then this one particle's density matrix contains exactly the information from the true many-body state that you still need to compute the expectation of this one-body observable. Okay, so as long as you're only interested in one-body observables, the one-body density matrix is the only object that you need. Okay, what then does condensation mean? Or in this case, in this talk, I'll talk about complete Bose-Einstein condensation. It means a complete BC into a one-body state means that the inner product of phi with gamma n applied to phi converges to 1 in the limit n to infinity. Okay, this means that the probability of finding a particle in the state phi converges to 1. Or in other words, up to a fraction which is negligible in the limit n to infinity, all particles occupy the same one-body state. And just as a side remark, it's well known that this convergence, in this case, is equivalent to saying that the one-body density matrix converges in trace class to the projection onto the state phi. So this statement, you can also ask, is it true in the GP setting? And it has been proved a while ago by Lieb and Saringer in a first paper in 2002 about the ground state, which was then very much generalized a couple of years later. It has also been revisited by Nam, Rougerie, and Saringer in 2016, where they proved that whenever you have an approximate ground state, meaning that to leading order, the energy of your state that you consider converges to the leading order of the ground state energy, then you have complete BEC into the minimizer, the unique positive minimizer of the GP functional. Okay. Okay, so these are well-known results. The next natural question you can ask then is, we have the leading order of the ground state energy, what would be the next order? What is also the rate of condensation? This is maybe more of a technical interest. I'll comment on this later maybe. And then the most important question for this talk I want to talk about is how can we determine a spectrum above the ground state energy? Okay. So let me first comment on the next order. Nam just mentioned this. There's a recent work from last year by Nam and Nachtergaele, Rico-Trier, where they proved on the one hand an upper bound on the ground state energy. Ground state energy is bounded by n times the minimum of the GP functional plus an order 1 constant. Okay? And also, under the assumption that the scattering length A0 is sufficiently small, they also prove the corresponding lower bound. This is this operator lower bound, the main result of their paper. We see that they get the operator bound Hn is greater than n times the minimum of the GP functional. You have this positive operator here, which projects onto it's the second quantization of the projection onto the orthogonal complement of phi GP. And you still have an order 1 contribution, which, is just an unimportant constant at this point. Under this smallness assumption, what this means, what this operator inequality implies, is that actually the ground state energy is given by n times the minimum of the GP functional plus an order 1 contribution. And if you have an approximate ground state, for instance, in the sense that the expectation of Hn is bounded by this leading order term plus a constant c, then you also get a rate, and this in fact is the optimal rate for the condensation. So the expectation of the one particle density matrix with respect to the GP minimizer converges to 1 with a rate 1 over n. Okay? The first result I want to mention is what we posted a couple of months ago with Benjamin and Severin, which is a proof of this operator inequality in this setting without a restriction on the size of the scattering length. Okay, and this it generalizes previous results we obtained with Chiara Boccato, Serena Chinatiempo, and Benjamin Schlein in previous years for the translation invariant systems. Okay? Maybe I should also mention that the techniques are rather different. While I said our work is a generalization of the previous work with Boccato, Chinatiempo, and Schlein, the approach of Nam, Napiorkowski, Retour, and Trier was to kind of adapt a nice argument of Brezke, Søren Fournet, and Solovey, which they developed in the proof of the Li-Wang-Yang formula we heard about. They adapted this to the inhomogeneous setting with the trapped particles. Okay. All right. So let me then come to the higher eigenvalues of the Hamiltonian. The last question I want to talk about. It's a bit more evolved to formulate it. Again, I would like to motivate a bit the heuristics, referring mostly to a result by Robert Seiringer and Greg from 2013. To motivate how to determine the higher eigenvalues of the Hamiltonian, let me switch to a simpler regime for the moment, to the mean field regime. And what I'm doing here is just I take this very singular delta-like interaction n to the 3 b squared, and I replace it by an unscaled potential v. You can think of it again as a bounded function. It's repulsive. One should also assume it's of positive type, but that's not so important for the presentation here. What we just see is that we still have this 1 over n, so that potential kinetic energy is of the same order. But this potential v here is now unscaled, so it's not as strong. Now we have long range and weak interaction. In this setting, you can formulate analogs of the results I just mentioned. Okay, for instance, the ground state energy per particle converges to the minimum of the so-called Hartree functional. You replace this quartic nonlinearity by a convolution term with this interaction potential v. You can also show with optimal rate that approximate ground state exhibit complete condensation into the minimizer of the Hartree functional. And you can also determine the excitation spectrum. This was dealt with in an important paper by Greg and Seiringer, and this is what I want to explain a little bit. So if one wants to understand how to determine these higher eigenvalues, it's useful to expand an expectation of Hn with respect to a many-body wave function around the leading order term of the energy. This makes sense. We want to understand the fluctuations around this energy. Okay, and one way to do this is, by now, a well-known observation from a paper Levi-Nam, Sefati, and Solovey. You can take your many-body wave function psi n, and you can expand this around the pure product function phi h to the n. Phi h is now the minimizer of the Hartree functional. This is just you can think about it like a decomposition when you write psi n as suitable basis. Phi h is one of the basis elements, and then you see psi n has one component which is proportional to this pure product state. Then you go on, you have one particle, alpha 1, which is orthogonal to phi h, and you have n minus 1 particles living in the state phi h, and then you keep going, you end up in a state alpha n, a component in which all particles are orthogonal to phi h, and this defines a a so-called excitation vector with components alpha naught to alpha n. And this map that sends psi n to this excitation vector is actually a unitary map. It maps L2s of the n to this excitation Fock space, which is just the Fock space built over the orthogonal complement of phi h, and you truncate it because you can have at most n excitations, because all the time we just consider states with n particles. So also at most, you can also have at most n fluctuation particles, excitation particles. In this Fock space, you can introduce a so-called number operator. You can measure how many excitations do we have. It's just a multiplication. In the small n sector, you just multiply with the number small n. And then it turns out it's a simple computation that complete BEC of a many-body wave function psi n is actually equivalent to saying that the number of excitations on average is much smaller compared to n. Okay? This means that all particles are essentially living in the state phi h in this case. Okay, so when you use this map u phi h and you transform your Hamiltonian in this mean field setting, then an important observation in this paper of Greg Saringer is that this transformed Hamiltonian gives you a leading order of the energy. You have a quadratic Fock space Hamiltonian, which is here in the first 3 lines, and then you have an error, which I wrote here as O of n to the 3/2 divided by n to the 1/2. The important thing that you should note, this is a bit technical, but the important thing that you should note is that if you can control this n to the 3/2 on the states that you consider, so low energy eigenstates, then this term here is just an error. And the spectrum of the many-body Hamiltonian is determined by this quadratic Hamiltonian. The nice thing is that quadratic Hamiltonians can be diagonalized exactly. Okay, so the strategy in that paper is making Bogoliubov strategy rigorous. You prove condensation. This way you can control this n to the 3/2 over n to the 1/2 rigorously. You can throw it away in view of the spectrum, and afterwards you diagonalize this quadratic Hamiltonian. Okay. To state the result, let me call by VMF, MF always referring to the mean field, this operator with kernel phi h of x, v of x minus y, phi h of y. Then you define a one-body Hamiltonian, a Hartree Hamiltonian, minus Laplace plus v external plus this convolution term, minus epsilon h. This is just the operators coming from the linearization of the Hartree functional. The epsilon h is its ground state. So ground state is, if you see this as a one-body operator. And then the statement in their paper is that the spectrum consists of finite sums nj, ej, mf, where nj is just the natural and ej, mf denote the eigenvalues of this operator eh, a square root of hh to the 1/2 times Hartree Hamiltonian plus 2 VMF, and then another factor hh to the 1/2. Okay? This may look a bit complicated, but this is really just coming from the fact that you have this inhomogeneous setting and you want to diagonalize this quadratic Fock space Hamiltonian. Okay, so it's just it's not a trivial computation, but still rather straightforward, I would say. Okay. The last result I want to present is what happens now compared to this result in the Gross-Podolsky regime. So if we switch back, we again exchange this regular interaction V by the delta-like interaction n to the 3 V scale n. Then it has been conjectured in the work of Greg and Saringer that an analogous result should also hold true in this GP scaling. Okay? And the idea is simple. I mean, if you think about the first part of the talk, what we have learned is due to the correlations, we have to insert these correlation function f. And we should think of taking the corresponding result from the mean field regime, replacing the regular interaction by a delta-like interaction, but you have to modify the mass of this delta interaction. You cannot just take n to the 3 V scale n, but you should also take into account the correlations which cause the change of this mass. So what you have to do is to replace this V mean field by a factor 8 pi a naught phi squared, just multiplication by this function, and limit n to infinity. And the Hartree one-body Hamiltonian you place by a corresponding Gross-Podolsky one-particle Hamiltonian, and then you should be able to prove that you have the corresponding statement with these replacements in a GP regime. Okay. So that's the second result I want to present. This is what we prove under suitable assumption on external potential and interaction, the spectrum of the Hamiltonian in the GP regime minus its ground state energy is given by finite sums of the form Nj, Ej, Gp. And Ej, Gp are precisely the eigenvalues of this analog one-body operator you get from the mean field setting by making the replacements I described on the previous page. Okay. Also here, let me add some remarks. First of all, again, it's a generalization. I mean, both works are a generalization of our previous work with Boccato, Chinatiempo, and Schlein for the translation invariant case. And as Nam also just mentioned, this statement 1 was just proved independently also in a recent work by Nam and Trier, like roughly a month ago. Okay. As a final remark, I want to mention that our proof also provides a formula for the ground state energy. This looks a bit complicated, it's a bit horrible. Just one takeaway from these two formulas is if you look at the formula, you start with n times the minimum of the GP functional. You get an order 1 correction. I mean, you get a couple of order 1 corrections. You can show that this operator here in brackets in this trace over the orthogonal complement is trace class. So this trace is finite. So it's a order 1 quantity. And all these terms here only depend on the GP minimizer phi GP and the scattering length. Okay, and the same is, of course, true if we look at the excitation spectrum. The excitation spectrum only depends on the interaction through the scattering length. Okay? So the same is true for the ground state energy. And you can see this formula here as an analog of the Li Wang-Yang formula we heard about earlier today in this Guls-Betaevsky regime. Okay? All right, so at this point, I think this is all I wanted to present. Maybe if you have some questions, I'm happy to answer them. Thanks for your attention, and thanks again for the invitation.
Thank you very much. Are there any questions or comments? Yes, please.
So I have a simple question. So if you, with 2, suppose you just take the harmonic trap, have you computed explicitly?
No, we haven't. Sorry.
But it should be doable, right? As an exercise, maybe?
Well, you have to compute the phi GP, right? You still have this. You still have the quartic interaction in the GP functional, right? Of course, you have the spectrum of minus Laplace plus V external. Now, if you have this quartic term, not sure if you have an explicit wave function. I have to think about it. I doubt it.
Oh, okay. Thank you.
Any other questions, either in the audience or online? Marcin?
So does your proof follow the strategy with cubic transformation, quadratic transformation, or do you have to go beyond cubic ones?
No, so the strategy is essentially the same, that's correct. I mean, energetically, nothing changes if you go from translation invariant to the trap case, of course. I'd say the difficulties is rather related to the fact that in the translation invariant case, of course, just if you look at the operators, HGP, for instance, essentially just minus the Laplacian, external is just a 1 in the box. The minimizer is just a constant 1 function. You can use the Fourier transform. And in the inhomogeneous setting, you have to compute then like a lot more commutators, say, just because these operators don't commute. Phi GP is not just a constant, and these tools kind of are lacking. From the moral point of view on this thing, on the technique, I think the strategy is the same. You need to do the quadratic conjugation to get the correct leading order, and then you know that the cubic term is still order 1, so you have to do a cubic transformation. But that remains essentially the same.
Okay, I don't see any further questions. Before we thank Christian again, I actually have to remember to hand over the medal for invited speakers. Oh, yeah. Silver plate.
Thank you.
Thanks again for the nice talk. And we can more or less continue right away after just changing slides. Very good. So while I think the slides are being put up, let me use this occasion to present the silver medal I see on a silver plate to Bruno Nachtergaele.
Well, thank you very much. I was hoping for gold. But,
Next time. So he will give the last talk of this session this afternoon on the stability of gapped phases and automorphic equivalence. I don't know if you want to use
thank
this.
you. Yes, I will try to use it. Well, thank you very much, Robert and Stefan, for organizing this session and for giving me a chance to be part of it. Better, I thank you now, because later you will cut me off and there will be no time for such niceties anymore. So I realized that I made a small change to the title. It probably got infected by Wojciech. But it's still the same meaning, so it's a more or less general title, Stability of Gap Phases and Automorphic Equivalence. I'm not going to cover this entire topic. Rather, I would like to focus on three recent results, two jointly with Robert Sims and Amanda Young, and then one in another paper with Jacob Birnberg and Peter Milbacher and Daniel Ulci. And I would like to highlight that a lot of the work has been done by the two excellent junior collaborators here. There is Amanda Young and Peter Milbacher. Peter is a PhD student of Daniel, and Amanda is a postdoc with Simona Warstel in Munich. So here is an outline. I've talked about this topic. It's a big topic. There is in principle a lot to say. So I'll focus on three new theorems, but I have to sketch a little bit of context, and I usually also try to give an idea of at least one element of the technical setting that allows you to prove things like this. And in this case, I'm going to emphasize notions of locality, quasi-locality, and almost locality in the quantum lattice systems that plays a role in here. And then hopefully I can sort of illustrate what these theorems really mean if you try to investigate a particular family of models and look at their phase diagram. And I will be able to show what the new results are that result from the application of these theorems. So here is quantum lattice systems. I'm sure you have recently seen what this means. Let's see. Okay. So lattice, it could be ZNU, but there are really interesting applications when you do something more general. And so the Delaunay set embedded in our NU would also be good. So then we have a finite dimensional square matrix algebra associated with each side of this set. It's a discrete metric space. Tensor products gives you the observables of a finite collection of spins. Say, here they are. They are naturally embedded in each other. So if you take the union, you get the local observables. And we complete it to get the quasi-local observables. So when we talk about a system, we define it through its Heisenberg dynamics, which of course you can do by defining Hamiltonians. I'm interested in discussing infinite systems, really, and there's different ways of getting there, but I'm not going to go in any kind of details. So you should think about an interaction phi x, which is an assignment of a self-adjoint term for each finite subset in the lattice that can be used to define Hamiltonians. And then what we really want is the infinite volume dynamics generated by a derivation, which is really the commutator with the Hamiltonian, and if some mild conditions on the interaction phi will guarantee that this is a well-defined operator. So here it is, delta of A. If you plug in a local operator, it's easy to see how to get this well-defined, then the dynamics is just a solution of the Heisenberg equations for that derivation. Formally, the solution is given by the exponential of the generator. So this is the Heisenberg dynamics given as a one-parameter group of automorphisms of the algebra of observables. And of course, for this to be well-defined, you will have to require some sufficient decay on these interactions, and I will come to that exactly in a moment, so that you know that the generator delta on the local observables is closable, and you can exponentiate it, and you get a proper group of automorphisms. And what you immediately see from this formula is that you could take the local observables and with rather weak conditions have this operator well defined on a dense domain, but it will not be an invariant domain. An invariant domain will necessarily be strictly larger than A. If you exponentiate, you get quasi-local observables. On the other hand, the quasi-local observables will generally be too much. This is an unbounded operator. It will not be defined on all of them. And so this is one way to introduce sort of the notion of locality, quasi-locality, and almost locality that plays a big role in the analysis of these models and the proof of some of the theorems that I will mention. So to give this a little bit of concrete content, so consider the fact that the quasi-local observables are obtained as a completion of local observables. So by definition then, for every A quasi-local, there is a sequence of strictly local A's that converges the norm to it. But it will be useful to sort of measure how fast this converges, and in many cases also to construct an explicit sequence of local observables that approximates the quasi-local one. And one very convenient way of doing that is using conditional expectations, P lambda, so for every subset of the lattice, I can take the partial trace over the complement of that subset. It's applying the tracial state on the complement and leaving the observables in the set lambda alone. So this is this map. It's a projection. And for instance, we can take a sequence, lambda n, that increases monotonically to gamma. For instance, a sequence of balls centered at x of radius n. And then, by the definition of the quasi-local algebra, you will find that the difference between A and this local approximation supported in the finite set lambda n, for instance, a ball, will tend to 0. And so there is a function fn that I can make monotone decreasing to 0 if I want, that satisfies this inequality. So now an idea is to fix a sequence of increasing sets like we did, maybe balls, but then also fix an f ahead of time, that something we have in mind. We want the rate of approximation to be of a certain speed. So this is a positive decreasing function, limiting to 0. And then I define a subset of the observables determined by f as all those that can be approximated using the conditional expectations so that the rate of approximation is given by this function fn. And so different functions f, different rates of decay will give me different subalgebras. You can show their star subalgebras and so on. So this is relatively straightforward, but you may wonder how you determine what the rate of approximation is for a given observable. And for that, it's sort of interesting to realize that this rate is exactly the rate that is measured by taking commutators. And so, for instance, if A is a time-evolved observable, then the norm of the commutator of time-evolved observable with an observable B, which supported here, this B is supported in the complement of lambda in the whole lattice, that's exactly the kind of quantity that Lieb-Robinson bounds allow you to estimate. And so that's how Lieb-Robinson bounds come into this game over and over again, because they do exactly this job of measuring the rate of locality. Okay, so let's make things a little bit more concrete, for instance, if I have nice Delaunay set as my the discrete metric space, then you can assume actually that these interactions is just supported on balls, Bxn, and then I can define a norm on the interactions by specifying a decay function and a uniform constant by saying that the norm of terms that are supported in balls of radius n have to be bounded by a constant by this function Fn. And it's a little bit of work, but really not very much. It's relatively easy to see that if you pick suitable functions, you'll be able to show that the derivation that generates the dynamics acting on an A, say, and an AG, will be in a H for another suitable function H if your interaction satisfies this with the bound F. So by playing with these functions, you can construct invariant domains, or at least you can determine what happens to them when you apply this kind of operator. Some functions that you can use, for instance, are stretched exponential functions, and in the theorems that I will show, this is the choice we're going to make. But there's many other choices that you have good reasons to make in other contexts. So this is used in quite a few applications and also applicable to other quasi-local operators that map local observables into quasi-local observables. And I have some references here where interesting applications using this kind of language have recently appeared. So I want to talk about ground states. Well, the definition of ground state here was shown to us by Yoshiko Ogata in the first lecture of the conference. I don't know, but you're there, hopefully. So the fact that a ground state is a state that minimizes the energy locally is expressed by this inequality. And so the derivation, the generator dynamics, appears here. So these A's have to be in the domain of delta. But in fact, again, by using these algebras of almost local observables, you can, all the cases that we consider, these are going to be cores for delta, and it's sufficient to check this condition on a core for delta. Easy to see that it will then be satisfied on all of the domains. So in practice, you work with a core of observables that are convenient for your analysis. And then to study the spectrum of the infinite system, you need the Hamiltonian of the infinite system, and the standard way of getting to that operator is by using the GNS representation, which is a representation of the algebra of observables on a Hilbert space in such a way that the state is given by a vector state in the Hilbert space by this formula. So this is representation pi, and then a vector omega, so that expectations of A can be calculated as expectations in the vector omega. And I'm not going to give any details here. There's not enough time for that. But what you find then, that is the dynamics is implemented in this representation by a strongly continuous unitary group of unitaries, which is then generated by a self-adjoint operator, and that's the Hamiltonian of the infinite system. So here is the Hamiltonian of the infinite system, which you can normalize such that the ground state is in the kernel, zero energy, and the Hamiltonian itself is a non-negative operator. If you are in a situation where the ground state is unique, this will then automatically mean that the kernel of this operator is one-dimensional. It's just spanned by this vector omega. I mention this because we're going to be interested in the spectral gap above the ground state, because we are interested in the problem of gapped phases. And I will tell you in a second what that is. The spectral gap is the spectral gap of that Hamiltonian. And this you can also express as a sharpening of this ground state inequality, which says that the left-hand side has always to be non-negative. But if you impose that it has a lower bound of this form, some positive constant gamma times the expectation of A star A for any A that has zero expectation, then there's just an expression by the variational principle that the Hamiltonian has no spectrum in the open interval 0 gamma. And so then the gap itself is the supremum of the gammas for which this holds. And you can do this for infinite systems on Zenu, say, and then that gap will be the bulk gap If you're interested in edge excitations, you would define the system on a half space, for instance, and then you would see the edge excitations appearing as the spectrum of the Hamiltonian defined in that particular system. Okay. So gapped ground state phases, what's that? So now we consider a large family of interactions. So we have fixed the algebra, we fixed the dimension of the spins, but we consider collection of interactions that maybe we have specified. We want finite range, which is what Yoshiko Ogata was talking about, but we can also take a Banach space of interactions defined by a certain norm that specifies the decay. And let's denote the set G as the subset of interactions such that we have gapped ground states. And it's about a family like that that we are interested in, and we define an equivalence relation on the interactions. Namely, two interactions phi0 and phi1s, which will generate two dynamics, are called equivalent if I can see them as the endpoints of a continuous or differentiable curves of interactions in this set G. And it depends a little bit how you define the norms, whether you have to say continuous or differentiable. It's not very important for the general discussion that I aim at here. And you require that along this curve, in fact, there is a uniform lower bound for the gap. So the dynamics generated by phi s for all s in the interval 0, 1 as a gapped ground state with a gap that is bounded below by a constant. So this notion of equivalence we introduced in almost a decade ago in a paper with Bachman, Michalakis, and Sims. And it is really just a mathematical version of what in the physics literature had before appeared as the notion of gap phase in a very well-known paper by Chen, Gu, and Wen. Here is the reference. And now, so the point is that this definition is in fact equivalent to another one that you see in the literature, which focuses more on a property of the associated ground states. In fact, it turns out to be equivalent to requiring that there is a dynamics generated by some kind of auxiliary time-dependent interaction, which I've called psi here, and it's not the real time dynamics, and that's why I call it alpha psi instead of, depending on the parameter s in 0, 1, instead of the tau t that defined the real time dynamics. And this interaction psi is one of these short-range ones, satisfying a decay condition of the same type that we just discussed. And the existence of this interaction curve of interactions phi that interpolates phi0 and phi1 is equivalent to the requirement that you can find an alpha psi s like that that interpolates the ground states. So the ground state at parameter s is simply the ground state at value 0 composed with this automorphism. That's why we call it automorphic equivalence. And it's important that this automorphism is generated by short-range interactions, because you can always find an automorphism that does the trick, but generically it would be one that has very poor locality properties. So the other word that I was talking about is stability of gapped phases, and so proving stability of a model or gap ground states means showing that they belong to an open set in that family G that is under consideration. That means that you can take any interaction in that family of sufficiently fast decaying interaction and add it with a small coefficient. You get a new model, you get new ground states, but they belong to the same phase. So that's what we mean by stability, and a lot of effort has been put recently into, recenter it, improving stability in various contexts, and I have some references here. I won't have time to discuss any of it in detail, so let me move on. So what are these three new theorems that I wanted to talk to you about? Well, here they are. It is about stability. So it is about a situation where you start from a model, the unperturbed model, which you will assume is finite range and frustration-free, and then add to it with a small coefficient s an interaction with fast decay of the type that I just discussed. And the question is whether this whole family of perturbed models remains in the same gap phase, assuming that the unperturbed model in the gap phase. And so I have the sort of the conditions summarized here. So I'm starting from a finite range frustration-free interaction and assume it's uniformly bounded. And so these hx's are supported in a ball centered at x of a fixed radius r. I'm going to assume that the finite volume Hamiltonians, so if this lambda is a ball itself for the unperturbed model, I may have low-lying states. So if I have edge modes that aren't exactly zero, I don't want them to be too small. And so this says here that the gap has to be bounded below by some power law. Any power law will do. That's an assumption. I don't have to assume the finite volume Hamiltonians are gapped. This is the new piece in these theorems. The infinite system, I assume, is gapped. I have a bulk gap. I'm going to take stretched exponentials to quantify the decay of the perturbations that I allow. And I will assume this LTQO condition, which basically says that if you may have many finite volume ground states, but they should all exactly look the same. And this is expressed by the fact that if you take a local observable and put it in between the ground state projections in balls at centered at x of radius m, where the observable, say, is at a fixed ball dxk, then as m tends to infinity, this simply goes to the expectation in the ground state times that projection. And this decay, this convergence is quantified by a function g, and I want this function g to converge fast enough so that this combination is finite. It is the power q of the gapless modes appears in there, and also nu, the dimension of the lattice that you started from. All right, so if you have these conditions, you have theorem A, which I could say much more about, and there's more detailed information, but the central message is that if these four conditions are satisfied, then by taking S small enough, and you have an explicit constant beta that tells you what small enough means, then you will have a gap that is at least gamma for any gamma. And you can do this for any gamma that is of less than the gap of the unperturbed model that you started from. So that is simply put, stability of the bulk gap for this class of systems on the infinite lattice. So now, there is the important topic of SPT phases, and I'm not going to talk in detail about that. But you may have the situation where you don't have a unique ground state, and you're not going to have this LTQO condition because it implies uniqueness. But you may have symmetry breaking. And so if a finite symmetry is broken, you have a finite number of disjoint ground states. And then you cannot have LTQO, but you can have LTQO. You can have this condition C4 for observables that are covariant or invariant under this symmetry. And if you then add to that the condition that if you take ground state projections or support projections for these disjoint states for two different states, and you put an observable in between, as m increases now, you get convergence to zero. So this also, again, becomes diagonal in the space of ground states that you have. And then basically you have the same stability theorem now with this discrete symmetry breaking taken into account. It's in a long paper it's going to appear in Rara and Poincaré. It's 119 pages, but it's a very nice theorem, I think, that under these conditions with C4 replaced by C4 prime, again, the gap is stable in each of these pure ground states, and the structure of the simplex of ground state with discrete symmetry breaking is also preserved for small perturbations. And so for each of the symmetry broken ground states, there is a family that you obtain by applying, again, a quasi-local automorphism. And it's the same automorphism that does that for all of them. So the whole structure of symmetry-broken ground states is preserved. The third result is a little bit of a different nature. It's for a specific family of models, and they're nearest neighbor spin chains for n-dimensional spins. Here is the Hamiltonian, and the nearest neighbor interaction is a linear combination of two operators. It's a swap of the state at x plus 1 at nearest neighbors, and then there is a one-dimensional projection on a maximally entangled state as the other term. This, in fact, generalizes the bilinear biquadratic chain of which the AKLT model is a special example. And it was proved recently that the model with u equals 0 and v equal -1 has two periodic dimerized ground states. This was in a recent paper by Eisenman, Dominique Copin, and Simone Wartzel. And so we have a theorem that says that this dimerization is also stable, and you can prove dimerization, at least for n large enough, also for sufficiently small u. So here is this stated in a theorem. There is a lot more details available about this dimerization. But this is a result that is sort of more specific. There's no additional conditions because it's a specific model, specific perturbation. But the general theorems don't apply because this model is not frustration-free. And so you have to use entirely different techniques to obtain the stability, and I can't really say anything about it, but there it is. And so let me just conclude by showing you the phase diagram of that model. We can apply theorem A, theorem B, and theorem C, and I have no time to explain the whole history of the model. It has been studied a lot in the literature, and in the past, primarily using exact solutions. So, but the point we're talking about is the neighborhood of v equal -1 and small u. So this is around the point B prime here. And so previously it was known that at that point you have two dimerized ground states for every value of n greater than 3. And so what the stability result says there is that, in fact, there is a small interval around here where you have the same two dimerized, not the same ground states, but where you have also the phenomenon of dimerization and a spectral gap that remains open in some small interval around B prime, at least if n is large enough. And incidentally, there's another point on this phase diagram that generalizes the AKLT point where the model is frustration-free and theorems A and B apply. And it's kind of interesting that we have both, because for odd n, you have a unique ground state in that point, and for even n, you also have a dimerized phase, which is frustration-free. And so there, theorem B applies and shows that there's in fact an interval around that point where you have discrete symmetry breaking dimerization and a spectral gap. And so these are new results about this phase diagram that you get as application of these theorems that I just mentioned. And with that, I think I have to stop. Fortunately, I don't have conclusions, so I'm done.
Thank you very much, Bruno. We can still take a couple of quick questions. Yeah, Volker?
I have a question concerning the framework that you described in the first half. Is it possible to prove similar to proving uniqueness of Gibbs states for classical statistical mechanical systems that are not translation invariant in using your framework with Lieb-Robinson bounds the way you describe?
Well, people would certainly like to do that. And in fact, they would be very happy to prove that even in a translation invariant case, if you don't have finite range interactions, but you have one of these interactions that decay exponentially or stretched exponentially, I think everyone believes that you have uniqueness there too. But only a partial result is available. Many people have tried. This is an open problem. And I don't know whether anyone was talking about it here, but I don't know whether, is David here? Yes, there, high up. So there is a recent result that gives some information, but it's not for all temperatures, but it's a range of temperatures that depends on, I believe, the decay of the interactions in a quantified way. And I'm sure it uses Lieb-Robinson bounds, but it's not the complete result.
Any other questions or comments? Maybe online, Stefan?
Yeah, it's not online, it's my question. Thanks a lot for the nice talk. I was just wondering if there are any general or natural conditions that guarantee this local topological quantum order, which you assume.
I know a lot of examples, and the rate of decay is usually not an issue. If you can prove that you have it, usually this function is exponentially decaying, or even better. So it is some strong form of independence of boundary conditions. So if you stick to just a case where you have a unique ground state, it's sort of a strong form of fast disappearing of the influence of the boundary, like the Brownian type condition. General techniques now, so except in one dimension. So frustration-free models in one dimension, you can prove a general theorem. But it's also true for the Levin-Mann models and Kitaev's quantum double models and other models for which you would want to apply this theorem. But no, I don't have a general criterion, and in fact, it's something that people are thinking about and generalize it to more models. It's something that is also a robust condition. So once you have it for a model, something like that survives perturbations. Nevertheless, it's not entirely trivial to prove it. So I think it's an area where we may see some progress in the near future, and it's important.
Okay, so maybe it's time anyway to close the session. So I suggest we thank Bruno once more for the nice lecture.